Okay, so as I mentioned at the very beginning, this is kind of a long talk, but we already missed 4 minutes, so I will try to go a little bit fast in order to finish the full presentation. My name is krlosMata. I work at Polygon. I'm the protocol team lead, and today my presentation is about how to verify EVM execution inside the pessimistic proof. In order to do that, the presentation is divided into 3 different stages. The first one is kind of an introduction of what is basically the pessimistic proof. The second one is the new design that we implement in order to verify an EVM transaction. And the third one is the next steps. Most probably I will not have time to read those slides, but are just 2 slides. And basically the next step is some improvement features that we want to add into the pessimistic proof in order to improve it. So first of all, some introduction, some key components, core concepts on the pessimistic proofs. And the first of all is why we need the pessimistic proof. So we need the pessimistic proof because we have a single smart contract on layer 1, which is called bridge LXLY, ACK layer LXLY bridge, whatsoever. And basically this bridge has all the liquidity across all the chains that are connected to the ACK layer. And what we want is that a single layer 2 chain cannot spend the assets of other chains. So it means that the chains must not trust other chains. And how we do that? Quite simple. It's kind of a ledger. So in the pessimistic proof, we track all the token balances that are in a chain, and this basically means that those token balances could not be negative, could not be lower than 0. So it basically means that a chain cannot spend what it doesn't have. So we're going to check more in details how this works, basically. In the pessimistic proof, there are 2 key actions. One action is the bridge, and the second important action is the imported bridge. A bridge basically means that some tokens are leaving the chain. And then an imported bridge, it means that some tokens are entering the chain. So it's quite straightforward that you cannot do a bridge before an imported bridge happens, because you will not have on the ledger that I mentioned before those tokens over there. And how we track this kind of ledger? Usually, in the zero-knowledge ecosystem, we are using a Merkle tree. This tree, we call it local balance tree, and this local balance tree is basically a ledger, so it tracks all the tokens balances that the chain has. And as I mentioned, every time that there is a breach, there is some subtraction on tokens on this ledger. And every time that there is an imported breach, there is some addition inside this local balance tree. Besides this Merkle tree instruction, we have more Merkle trees. And those Merkle trees are basically the local exit tree and the nullifier tree. The nullifier tree is quite straightforward, and is basically to avoid double spending. So every time that there is an imported breach, we are going to mark it as that it has been claimed, it has been spent, in order to avoid double spending. And the local exit tree, it tracks all the breaches that has been done in a chain. Later on, this local exit tree will be shared with other layer 2s. So other layer 2s can claim the breaches that has been done on your chain. But it's not enough with the local exit tree. That's why we have the global exit tree, the global exit route. And basically, the global exit tree, what it does is it gathers all the local exit trees, which basically it's a Merkle tree, so it's a root. It gathers all the local exit trees, and it kind of aggregates them. It joins all of them together. And then we have another Merkle tree, which is the layer 1 info tree, which gathers all the historic of global exit trees. It means that with a single 32 bytes value, the layer 1 info tree, the root of that Merkle tree, with those 32 values, a chain can access all the breaches that has been done in all the chains on the ACK layer. And very convenient when you want to share breaches among layer 2 to layer 2, layer 1 to layer 2, or whatsoever. Okay, let's see the design of the pessimistic proof, the second version that we did a while back ago. And at the very end, the pessimistic proof, it's a zero-knowledge circuit, so it's a program, basically, that has some constraints. And you can think about the pessimistic proof and an EVM state transition proof. So you have some initial state, you have some transactions, and when you apply those transactions in the initial state, you have a final state. On the EVM, you have an initial Patricia-Merkle tree, some transactions, you apply to them, and you have a final state of the Patricia-Merkle tree. So here it happens exactly the same. You have an initial state, which is defined by the trees that I showed before. And those trees are the local exit tree, the local balance tree, and the nullifier tree. And then you apply some transactions. Those transactions, in the context of the pessimistic, are basically the breaches and the imported breaches I explained before. And then you will get a new state of the pessimistic. Okay, let's see what the circuit does. Well, I would say this is quite straightforward, but then on the circuit, there are three different stages. We apply the breaches, we apply the imported breaches, and then we verify a ECDA signature. This will be very important in the upcoming version. When we apply the breaches, what we are doing is to move forward on the pessimistic state transition. And every time that we apply a breaches, as I mentioned before, we are adding one leaf to the local exit tree. And also at the same time, as I mentioned before, every time that we apply a breach, it means that we are subtracting some value from the local balance tree. And here, this is just an example that on the old pessimistic, on the old local balance tree, we have 10 ether, then we subtract 1 ether, which is quite a straightforward example of a breach of 1 ether. And then the second stage is that we apply imported breaches. Those imported breaches affect, as I mentioned before, on the local balance tree and the nullifier tree. So first of all, we need to modify the balance of that given token. For example, in this example is 66 pol. We are subtracting, we are adding that balance into the local balance tree, and on the nullifier root, we are basically set it kind of as claimed. And let's go for the third one. In a layer 2, if you have an initial state and you want to go to the final state, who can basically propose the transaction as data availability in order to move from the initial to the final state? So this is basically the sequencer. And here it kind of happens the same. Who is able to move forward on the state transition on the pessimistic proof? And we have somehow this is a sequencer. So basically, a sequencer is basically an address that the chain can define on layer 1. And basically, this address, the signature of this address will be checked on the circuit. And of course, it needs to match with the one that has been set on layer 1. That's why we have defined super simple approach, which is consensus type and address. Consensus type means that in the circuit, we will do an easy recover. And in order to forward those values into the circuit, we just hash it. And then we make what we call the action hash. This is on layer 1. Exactly the same thing we will be doing on the circuit. And this is basically a public input of the pessimistic proof, and they need to match, otherwise the proof will not be correct. Okay, so what happened with such an approach? This approach is not enough modular. What does it mean is that imagine that a chain does not want to use an easy recover, an easy DCA signature, in order to move forward on the pessimistic state transition. Imagine that a chain wants to add another signature scheme or a multisig or whatsoever. It means that inside the pessimistic proof, we will need to add some kind of new code with a new consensus type in order to allow that chain to work. It means that basically the chain cannot choose whatever the chain wants in order to move from the initial state to the final state. And this is problematic because basically the chain depends on us. No? So we provide, in this case, an easy DCA, and maybe we will add another consensus type. And the chain needs to choose between one of them. That's not enough modular, and does not give freedom to the chains. So the version 3 tries to give some sovereignty to the chains. And basically the version 3, what tries to do is it introduce a new concept, which is a generic action. And basically what we do is we verify a zero knowledge proof. Again, inside a zero knowledge proof. And basically this gives full freedom to the chains, we are using basically SP1. And it also, the new design also has backwards compatibility with version 2. We'll see in the following slides. And this is the version 3, I would say, summary or overview of the circuit. As you can notice, the public inputs are exactly the same, but we only have one addition here, which is dealing with consensus type equal to 1. And instead of doing, here we are doing SDCA. Here we can do, I don't know, multisig or another signature scheme. Here we are verifying a zero knowledge proof. And by verifying a zero knowledge proof, we are saying that the chain can verify whatever zero knowledge proof that the chain wants. So totally freedom to the chain. And how we can achieve that? We introduce a new consensus type, and we are hashing now two fields, the action key and the action params. And basically, the smart contract builds the new action hash, which is the keycag of the consensus type, action key, and action params. Here, the nomenclature is very similar to the one that is using SP1, because as I mentioned, we are using SP1 verifier. And the good thing about that is that inside, we will see later on, but inside the action params are the public inputs that the chain wants to verify on each zero knowledge proof. And the pessimistic proof is fully agnostic to those parameters. So it means that the pessimistic proof does not care about what the chain is going to be verified. And we will see later on as well, the action key basically defines the circuit that the chain wants to verify. Okay, and this is kind of the code inside the pessimistic circuit. As I mentioned, it backwards compatible, so if consensus type equals to 0, this code is exactly the same as the version 2. But if consensus type is equal to 1, what we are doing is to building the inputs for this zero knowledge proof, and those are the public inputs, which is the SHA of the public inputs of the pessimistic concatenated with the action params. And then we are verifying a zero knowledge proof. And basically, if we use one library in Rust, which is sp1.verify, we need to provide the public inputs and the action key. The action key defines the circuit. This is very important. What is inside, as I mentioned before, what is inside the action params, the pessimistic proof does not care at all. We will see later on. And then the circuit, of course, builds the action hash, and the action hash is a public input of the pessimistic proof, so we need to match with the one that the smart contract has built. Okay, let's get, now we saw how we change the pessimistic proof, and now we can not just only verify an ECDS signature, but we can also verify a zero knowledge proof. Okay, let's get inside that zero knowledge proof. As I mentioned before, in the pessimistic circuit, we are doing sp1.verify. And one of the parameters is the action key. And the action key, as I mentioned before, it defines the program that the chain needs to verify. And this program, we call it action params. And let's see how it looks like when we want to verify an EVM state transition. This is the circuit of the action programs, and the publics are built by the pessimistic, are the ones that I showed you before. So it's the publics of the PP plus action params. And what this action program does, it has two different stages. The first stage is to verify an EVM state transition, and I would say that the chain can verify this state transition as the chain wants. We will see how. And also we have the bridge constraints. The bridge constraints are very important because the bridge constraints assures that all the bridges and imported bridges that happen on your chain matches with the ones that the chain is providing to the pessimistic. They need to match. Okay, so what happens, the actions that happens in your chain matches the actions that you provide to the pessimistic proof. So let's see one example, how to verify this EVM state transition on the action program. And I would say that the code is not super complex, but basically, and this is the action program. And in the action program now, inside the action program now, we provide all the necessary public inputs in order to verify this EVM state transition. This is not the pessimistic proof, it's the circuit inside the pessimistic proof. Here, of course, we need to rebuild the public inputs in order to match the public inputs that the pessimistic proof have computed. And basically, inside the action program, what we do is verifying another zero-knowledge proof. And this zero-knowledge proof basically verifies an EVM state transition. And those are the bridge constraints. In order, the bridge constraints basically are divided in 3 different main points. The first one is to prove that all global exit routes that we insert on layer 2 needs to exist on layer 1. And in order to do that, we just do a hash chain of global exit routes. And basically, this hash chain is stored on the smart contract at a specific smart contract at a specific storage slot. So with just 2 storage proofs, we can read the initial of the hash chain and the final of the hash chain. If we have the initial value and the final value, the prover must provide all the intermediate value in order to reveal that hash chain. And then we can get kind of an array of global exit routes, and that array of global exit routes, we can prove it against the layer 1 info tree. Also, the second point is the new local exit route. If we take the new state route at a given smart contract at a given storage slot, we can use a storage proof in order to read that specific storage slot, which is the new local exit route. And this new local exit route needs to match with the one that is defined on the pessimistic route. And then we do exactly the same with the imported bridges. And the imported bridges work exactly the same as the global exit route. We just do a hash chain with 2 storage proofs. And the most, I would say, important one here is this assert here and this assert here. Those asserts, as I mentioned before, is asserting that what happens on the pessimistic proof is exactly the same as what happens on a layer 2. If you kind of delete those asserts, a chain can do whatever they want on their state transition, on the EVM state transition, and kind of cheat the pessimistic proof. So those asserts are very important. And this is how the proof schema looks like in the final, I would say, flow. As I mentioned before, we use OP-succinct in order to verify this EVM state transition. The OP-succinct, at the very first stage, they create a proofs that basically validates some block range from block 1 to block 10, and so on. Also, the OP-succinct stack creates another proof that basically aggregates all block range. Thus, this aggregated proof is verified inside the action proof. And then the action proof is verified inside the pessimistic proof. And then the pessimistic proof is verified on layer 1. It's kind of an inception of zero-knowledge proofs. OK, let's see the next steps. As I mentioned before, this is the ActChain program. And imagine that a chain does not want to verify its EVM state transition using OP-succinct stack, but instead they want to verify with a totally different consensus. The thing is that we can kind of reuse almost all the ActChain program, and instead of verifying a zero-knowledge proof here, we can just verify a proof of work. We can verify a proof of stake, or whatever consensus do we want. It means that basically reusing the same circuit and changing some line of code, we can give more freedom, more sovereign to the layer 2 chains. And then also, as I mentioned before, we are using SP1 on the pessimistic proof in order to, and SP1 is the proving system that we are using. So the chain, I would say, must use SP1 in order to verify its ActChain program. And we want also in the future to add more proving systems. So the chain is not just only fully freedom to choose its state transition, but also it can choose the proving system that they use. So we can, for example, we are using now SP1, we can also use THISC, we can use RISC0, or whatever other proving system. I did quite fast, sorry for that. But I think I'm in time. I'm in time?
You're in time, but we don't have time for questions.
Well, we don't have time for questions, but if you have any questions, I will be out. So please feel free to reach me and ask me whatever question you have. Thank you very much.